So, we are going to discuss probability distribution function, or sometimes we say it cumulative distribution function. We know that there is a concept of random variable and there is an associated probability with this. Now, to understand the different characteristics of the probability distribution of this random variable, we need to study some interesting things. So, one of the most important such quantity is, or some factor is that which is known as distribution function. Basically, this itself characterizes the entire probability distribution corresponding to a random variable. So, we are going to discuss this random variable and especially the distribution function and its several properties, where we can use it, how does it look like, and some other theorems, important theorems which will be of real interest and which will be of immense importance in the entire probability theory. Now, we will discuss distribution functions. I have written distribution functions 1. This is the first talk on distribution functions, and we will have some more talks on this topic. We know something about the random variable, and in a very simple way we can think that a discrete random variable. Now, we all know that a discrete random variable has a probability distribution which is given by probability mass function. On the other hand, if we consider a continuous random variable, which is actually absolutely continuous random variable, we can have something what is called probability density function. Now, if you plot this probability density function on the vertical axis, we will have some idea about the probability distribution of this random variable, which is in fact absolutely continuous. Now, the question is, can we define something which is more general in case of discrete variable as well as continuous variable, or is there anything which is something similar between these two? The answer is the distribution function. This is a more general thing in the area of probability theory that really makes sense from a real life event to a probability structure. So, through a distribution function, we can think of probability of a particular event which is explained in terms of a random variable, be it continuous, be it discrete. So, the definition of a distribution function of a random variable we can define as capital F of small x, which is nothing but probability capital X less than equals to small x. This should be defined for every x belonging to minus infinity to infinity. Now, from the definition it is clear that whatever be the nature of random variable, we can always think of the event capital X less than small x, or we can calculate, we should be able to rather calculate the probability of this event that capital X takes the values which are less than or equal to small x. Now, small x is in fact a realization of the random variable based on a random experiment. So, the basic question is, so once we define a distribution function, the question is it possible to identify a distribution function? So, there are some remarks I should make in this context. Now, what is the meaning of identifying a distribution function? This means, suppose I give you one function, can you tell me whether this is a distribution function corresponding to some random variable, or it is not a distribution function? Now, naturally, to understand the distribution function, whether a function is a distribution function, we first need to study some of the properties of this distribution function. So, now we are going to focus on the properties of distribution function of a random variable. Now, we do not consider that the random variable should be discrete or should be continuous, it can be any random variable, and we are just going to discuss the properties or explore the properties of the distribution function of a random variable. So, there is a theorem. This theorem states that suppose x is a random variable, then its distribution function. Now, throughout this talk and the subsequent talks, by df we always mean that distribution function. So, now if x is a random variable and capital F x has the following properties. First property is that distribution function or capital Fx is non-decreasing in x. That means, if you take two values of x, one is x prime which is less than x, then capital F of x prime is less than or equals to capital Fx. That means, it is non-decreasing. It might be strictly increasing, but the general idea is that it should be at least non-decreasing. Another property, actually there are two properties in this B, which is capital Fx equals to 1 when you take the limit that x goes to infinity. That means, capital Fx f of small x goes to 1 as x goes to infinity. On the other hand, since we are considering the limit that x goes to infinity, so there might be some interest to see what happens when x goes to the lower limit of the random variable. That means, when x goes to minus infinity. And interestingly, this property explains that whenever x goes to minus infinity, then capital F of x goes to 0. And another most important and interesting property of this distribution function is that distribution function is always right continuous. That means, limit of f of x plus h when x goes to 0 plus, that means, when h approaches to 0 from the right side of 0 or from the positive part of 0, then it should be exactly equals to capital F of small x, and this should be true for every x belonging to this entire real line or on the support of x. That means, all the permissible values of x. Now, naturally one can ask question, is it possible that f is continuous? Well, f might be continuous, but for some random variables in some special situations, but it is always right continuous. Whatever be the nature of the variable is, it might be discrete, it might be continuous. So, these three properties are the most important or probably characterizes a distribution. So, whenever we know that suppose somebody gives me a function and claims that this is a distribution function, then I should be able to check all these three properties, that f must be non-decreasing. That means, for every x prime less than x, f of x prime is less than equals to f of x. F of x goes to 1 as x goes to infinity, and f of x goes to 0 as x goes to minus infinity, and we should be able to show that f x is right continuous for every x in the support of x. So, to prove this theorem, we need two other facts. These are very simple and known to us. First thing is the monotone property of probability measure, which states simply that if A is a subset of B, this will always imply probability of A is less than equals to probability of B. And another fact, which is nothing but a famous theorem based on probability measure, that is called continuity theorem of probability measure. It says if A n is a decreasing or increasing sequence of sets that decreases or increases to A. That means, if A n decreases either to A or A n increases either to A, then probability of A n goes to probability of A as n goes to infinity. So, this is the famous continuity theorem of probability measure, and to prove that a distribution function which is defined by probability capital X less than equals to small x and denoted by capital F of x, that is small x, we need these two properties to prove the three properties of distribution function that we have just discussed. So, the proof goes this way. To show that a distribution function is always non-decreasing, just note that if we consider the event x capital X less than equals to x prime, which must be a subset of capital X less than equals to small x for x prime less than x, that means this is contained in this set, then you consider this to be A and this to be B. So, A is a subset of B, then naturally by monotone property of probability measure, we can immediately say that probability of A less than equals to probability of B, which means probability of A is nothing but f of x prime and probability of B is nothing but f of x. So, f of x prime less than equals to f x. So, this proves the fact that f(x) or distribution function is always non-decreasing. Second one will be obtained through probability continuity theorem or probability measure. If we consider this event capital X less than equals to minus x, naturally as x goes to infinity, then this event, this set goes to null set, which is phi. So, naturally that means x goes to infinity means minus x goes to minus infinity. So, in other words, we can write probability of this event, which is nothing but capital F of x, this goes to 0 as x goes to minus infinity. Exactly in the same way, if we define capital X less than equals to small x, this goes to omega, there is a full set or the entire sample space as x goes to infinity, then naturally probability of this goes to probability of omega, which is nothing but 1 as x goes to infinity. So, hence the proof of these two properties, that capital F of x the distribution function goes to 0 as x goes to minus infinity, and it goes to 1 as x goes to infinity. Third one, the proof is very simple. Suppose h is greater than 0, h might be very small number, but strictly positive. Then you can write capital F of x plus h minus capital F of x, which is nothing but probability small x less than capital X less than equals to x plus h. But note that this event, that x small x less than capital X less than equals to small x plus h, this goes to phi as h goes to 0 from the positive side. So, again, so this event goes to phi as h goes to 0. So, we can immediately say that by continuity theorem or probability measure, that probability of this event, which is x less than capital X less than equals to small x plus h, goes to probability of phi, which is 0 as h goes to 0. Hence, we can immediately say that capital F of x plus h minus capital F of small x goes to 0 as h goes to 0, which in turn says that capital F of x plus h goes to capital F of x as h goes to 0 from the positive side. So, this concludes the proof of all the properties that a distribution function must satisfy. Now, there should be a natural question which comes very naturally, that whether the converse is true. That means, if I give you a function which satisfies all the three properties of this distribution function, can we claim that this function is nothing but a distribution function? That means, there must exist a random variable x for which this would be the distribution function. So, this is the meaning of converse. So, the question is whether the converse of the above previous theorem is true. Fortunately, the answer is yes. Hence, we can write one theorem in the form of a theorem which is nothing but the converse of previous theorem, which is theorem 1, which states that if capital F is a function that is defined on minus infinity to infinity, which satisfies the previous three properties, that is A, B and C of theorem 1, then there exists a probability space omega script f and p. Script f is nothing but the sigma field generated by the class of subsets of omega, and p is the probability measure defined on this omega and script f. So, there exists such a probability space and a random variable which is defined on this probability space, such that we can always write capital F of x equals to probability capital X less than equals to small x, which is usually denoted by only capital F of small x for every x in the real line. So, this theorem is a very important one to check whether a given function is a distribution function or not. So, on the other hand, if we show that a given function satisfies these three properties of theorem 1, then we can immediately conclude that there exists a random variable obviously defined on a particular probability space, for which f would be the distribution function. Now, let us consider some few definitions relating to this distribution function. First definition is that a distribution function capital F is said to be absolutely continuous if there exists a non-negative Borel measurable function f defined over minus infinity to infinity, that is the entire real line, such that capital Fs can be written as the integral minus infinity to x f t dt for all real x. So, if we are able to write capital Fx in the form, in this form, using another function which is non-negative Borel measurable defined over the entire real line, which is denoted by f, small f, then this small f t is known as the probability density function corresponding to the random variable, or corresponding to the random variable x, or corresponding to the distribution function capital F. So, naturally it is not necessary that every time we will get a probability distribution, but probability density function, but we can get a probability density function, or rather we can derive a probability density function only corresponding to a absolutely continuous random variable. Another definition is that a distribution function f might be continuous, f is continuous at x if probability of x equals to 0. That means, probability of observing a single point in the support of x, provided f is continuous, is exactly equals to 0. But the important thing that we should note, that this does not imply that f is differentiable at x, although f is continuous, but f may not be differentiable or at x or is derivative if dash f x exists. That means, it does not guarantee that you will always find a probability density function corresponding to capital F, but we can get only when it is absolutely continuous. Now, if probability of capital X equals to small x, at least for some x or some few values of x, is greater than 0, then we say that capital F has a jump of magnitude, and that magnitude is measured by probability capital X equals to small x at small x. There is a realization of x. This thing is known as probability mass function, or in short PMF. Now, we will just consider one example to show whether whatever we have learned is really useful, and whether we can use our learning to a real example. Suppose somebody gives you that capital Fx is this form, which is 0 if x less than equals to 0, 1 minus x to the power n if x lies between 0 and 1, and it is 1 x greater than equals to 1. So, if we see the properties, if we want to check the property, it is clear that for every x1 less than x2, we can immediately see that fx1 less than fx2. So, it is non-decreasing. Now, it is clear that fx equals to 0 at x goes to minus infinity, and fx equals to 1 as x goes to infinity. And if you consider the right hand limit of f of x plus h, just by little algebra we can show that it is nothing but equals to 1 minus x to the power n, which is nothing but fx, capital Fx. So, this proves that capital F satisfies all the 4 properties, or the 3 properties of a distribution function, and so we can say that there exists a random variable x for which capital Fx is a distribution function. So, naturally capital F is a distribution function because it satisfies all the properties in the theorem 1. So far we have discussed some basic idea about the distribution function, starting with the definition and why it is used. Then we have also discussed a few properties, or rather the most important properties which will characterize a distribution, and a very important theorem which will help us to identify whether a particular function is a probability distribution function or not. We have also discussed one example, so that you will have a very clear idea about how a distribution function looks like, and naturally depending on the nature of the random variable, the distribution function might be different, the nature of the distribution function will be different, but the entire thing can be unified under the framework of distribution function in a unified way. So, we will discuss in the next few classes how this unification can be done, what are the other important properties, whether there exists some kind of, whether we can think of some kind of convergence based on these distribution functions, whether we can define some kind of integrals using these distribution functions. So, everything we will discuss in the next few talks.